Hi guys, welcome to Chem or Chem. In this video, we are going to see Dienone-Phenol Rearrangement. If you are new to this channel, please subscribe. In Dienone-Phenol Rearrangement reaction, dienone, that means that 4,4-disubstituted cyclohexadienone can be converted into a stable 3,4-disubstituted phenol in the presence of acid. So next we move on the mechanism. Here you see that cyclohexadienone, that carbonyl oxygen has two lone pair of electrons that can readily interact with acid that generate corresponding this intermediate. Then after that, that electrons shifted to this carbonyl carbon, then followed by this electron shifted towards to the oxygen, since oxygen has positive charge, which leads to generate this corresponding carbocation intermediate, then followed by that one of the methyl group shifted to the carbocation center. Usually this shift is called 1,2 shift, which leads to generate corresponding tertiary carbocation. Now you closely look, this one is a secondary carbocation, now this one is a tertiary carbocation, then followed by removal of H plus ion by the help of water molecule present in the reaction medium, which generates the corresponding phenolic compound. So in this reaction can be considered as a reverse of phenol rearrangement reaction, since in phenol rearrangement reaction, alcohol compounds can be converted into the ketones, but in this case, dienone-phenol rearrangement case, ketones can be converted into the alcohol, that means phenolic compounds. Dienone-phenol rearrangement involves a loss of carbonyl bond and gain the aromaticity. In fact, we can say the gaining the aromaticity as a major driving force for this dienone-phenol rearrangement. Now we'll look about some important examples based on this particular rearrangement. So this question I have taken from IIC 2008 PhD entrance exam. So now you look this dienone, that fourth position has methyl as well as phenyl substituted one. When you subject under the dienone-phenol condition, that generates the corresponding phenolic compound. Here you see that phenyl group will get more migratory power compared to the methyl. So in our upcoming slide, we will see complete migratory aptitude of this particular rearrangement reaction. So in this particular example, phenyl group will get more priority compared to the methyl that generates this corresponding phenolic compound. So now you take this example. Here you see that this particular dienone has methyl as well as ester group. When you subject under the acid, now this is the question, which group will migrate, either methyl or ester. But before that, when you subject under the acid, you will get this corresponding carbocation intermediate. So after that, there are two possibilities. That first possibility is ester group will migrate, resulting that generate this new carbocation intermediate. Similarly, instead of ester, when you migrate the methyl group, you will get this type of carbocation intermediate. Now we should think about which carbocation is more stable, either this carbocation or this carbocation. We will see one by one. When you take this carbocation, can be stabilized by methyl group. That methyl group has 3 alpha hydrogen. Through 3 alpha hydrogen that can be stabilized by hyperconjugation as well as plus I effect. But when you take this carbocation, that one is attached with ester group, that here ester carbonyl oxygen has more electronegative atom that pulls the electron from the carbonyl carbon, resulting that that particular center has positive, as well as this carbocation center also positive. That is impossible to stabilize this carbocation by ester group, resulting that we can say this particular carbocation has more stable compared to this carbocation. So resulting that you will get this corresponding phenolic compound. So in general, we can say electron withdrawing group will get more priority compared to the electron donating group in order to the migration. So next we move on another example. In our previous example, we seen one of the group is electron donating group and another group is electron withdrawing groups. Then we can easily predict electron withdrawing group will migrate. But in this particular example, you see methyl as well as hydroxy substituted cyclohexadienone. These both groups are electron donating groups. So first you see generate the corresponding carbocation intermediate. Again, there are two possible shift. First, we will migrate methyl group. We'll get this type of carbocation intermediate. And when you migrate hydroxy group, you will get this type of new carbocation intermediate. Now we should think about which carbocation is more stable. So now you take this carbocation. Here you see this carbocation directly attached with hydroxy group. In general, oxygen is very good at stabilizing a positive charge on adjacent carbon through the resonance effect. In case of here, we already discussed about this methyl group. So methyl group can stabilize this positive charge by hyperconjugation as well as plus I effect. So these two carbocation, it seems to be equally stable. So when you face this type of situation, we should consider about this rule. So compared to this rule, this particular carbocation is more stable. Therefore, you will get the corresponding this product. So in general, we can say less electron donating group will migrate. So this is the another example. In our previous example, we seen all the examples are 4,4 disubstituted cyclohexadienone. Not only 4,4 disubstituted cyclohexadienone, even 2,2 disubstituted cyclohexadienone also undergo this Dienone-Phenol rearrangement. So when you subject under the acid condition, that probably generate these two type of carbocation intermediate. So first one, when you migrate the ethyl group, you will get this carbocation intermediate. This carbocation can stabilize by plus I effect as well as hyperconjugation. Since this methyl group has 3 alpha hydrogen that can stabilize this carbocation intermediate. So when you migrate methyl group, you will get this corresponding carbocation intermediate. Now this carbocation can be stabilized by hyperconjugation. Again, however, this hyperconjugation only supported by 2 alpha hydrogen as well as plus I effect has higher than the methyl. So again, when you get this situation, you should consider this priority rule. Resonance will get more priority. After that, hyperconjugation, then plus I effect. So here hyperconjugation will get more priority. Therefore, this one only the more stable carbocation, resulting that generates the corresponding phenol. So now you look this example. So in our previous example, we seen all the cyclohexadienones are symmetrical one, but in this case, unsymmetrical cyclohexadienone. So when you get this type of example, we should see the electronics of that cyclohexadienone. So we already know that carbonyl oxygen has high electronegative atom. Therefore, that pulls the electron from the carbonyl carbon, resulting that will get delta negative. So this center will get delta positive, this center will get delta negative, and then finally this center will delta positive. So similar pattern we can derive from this side also. Apart from this side, here this particular second position has hydroxy group that can undergo the keto-enol tautomerism, resulting that this particular center has more electron rich compared to this center. So resulting that when you subject under the acid, most probably carbocation will generate only this side. So after generate this carbocation, one of the methyl group will migrate to this center, resulting that generates the tertiary carbocation. Then followed by removal of H plus, that leads to generates the aromatized phenol product. After getting this phenol product, you should see the tertiary butyl group has highly sterically hindered group. So this one, it's really difficult to place near to the methyl group, because this methyl as well as tertiary butyl group should place in the planar form. So because of that highly sterically crowding, so this particular molecule quickly react with acid, so resulting that generate this carbocation. That means that H plus ions directly ordered into the tertiary butyl attached carbon. So resulting that generate this carbocation intermediate, then followed by that removal of tertiary butyl carbocation. That means that this carbon-carbon bond cleaved, that electron shifted towards to the ring, resulting that elimination of tertiary butyl carbocation that generates the corresponding phenol compounds. Here you see this starting material has tertiary butyl group, but finally that tertiary butyl group has eliminated as a tertiary butyl carbocation. So this is the another example. So just like our previous example, so instead of tertiary butyl, so this example has methyl group. So resulting that you will get the two type of carbocation intermediate. So we already discussed about this center, particularly slightly electron rich. Therefore, only the possible carbocation. This one, so resulting that 1,2 migration takes place that generates the corresponding phenolic product. So here there are no much sterically hindrance present in that particular molecule. Therefore, so methyl group doesn't eliminated. So this is another example. So here you see this particular example has allyl substituted orthocyclohexadienone. When you subject under the acid, you will get this type of carbocation intermediate. Then after that, you see how that allyl group migrated. So here allyl group will get more priority in the point of migration. So now you look, this carbon-carbon bond cleaved, this electron moves here. Then see simultaneously this double bonded electron attacks the carbocation, so which leads to generate tertiary carbocation. After getting this carbocation intermediate that quickly undergoes the Cope rearrangement reaction, you see this carbon-carbon bond cleaved, this electron moves here, this pi bonded electron attacks this pi bond, resulting that this pi bonded electron moves towards to the here, then followed by this pi bonded electron moves towards to the carbocation center. So which leads to generate this carbocation, then followed by removal of H plus ion, which leads to generates the corresponding para-allylated phenol. So not only 4,4 disubstituted dialkyl substituted cyclohexadienone, so spiro substituted cyclohexadienone also can undergo this Dienone-Phenol rearrangement. So this one is a symmetrical molecule. When you subject under the acidic condition, so that generates this type of carbocation intermediate, then followed by ring expansion takes place. Here you see this carbon-carbon bond cleaved. So this bonded electron moves towards to the carbon center, which leads to ring expansion takes place. So this one is a 5-member ring, resulting that generation of 6-member ring along with one tertiary carbocation. Since this bond broken, so resulting that carbocation shifted to this center. So this is the center. Then followed by aromatization takes place, which leads to generate the corresponding phenolic compound. So this is the another example. So this is one of the important example. Here you see how that reaction condition affect the selectivity of the product. For example, when you take this particular pyrocyclohexadienone, when you subject trifluoroacetic anhydride, trifluoroacetic acid, and sulfuric acid. In fact, this condition is non-aqueous acidic condition. When you subject under this condition, O migration takes place. Here you see this carbon oxygen bond breaks down. So this oxygen moves towards to the third position, resulting that generate this particular compound. When you subject the same compound in the aqueous condition, carbon migration takes place. For example, here you see this carbon bond breaks down. So this particular phenyl part migrated towards to the fifth center. So this is the another example how our reaction conditions influences the selectivity of the product. Here you see when you subject aqueous reaction condition, you will get the meta product. In case of when you use non-aqueous reaction condition, that means that acetic anhydride and sulfuric acid, you will get the para product. So now you will see about the mechanism. So here you see this fused cyclohexadienone. This carbonyl oxygen has two lone pair of electrons. So that one readily will protonate, which leads to generate this intermediate. Now that electron shift can take place two ways, either this side as well as this side. Now we will migrate in the top fashion. So here this electron moves here and this electron moves towards to the oxygen, which leads to generate this carbocation intermediate. Then followed by 1,2 migration takes place, that ethyl group migrated towards to the carbocation center, which leads to generate the tertiary carbocation. Then followed by removal of H plus, that means aromatization takes place, which leads to generate the meta product. So meta product means that, so this is the ipso position, this is the ortho position, here meta position. Our rearrangement takes place at the meta position. So when you run that same reaction under the non-aqueous condition, first two steps are mostly similar. After that second step, here you see this electrons shifted towards here, this electron shifted towards to the oxygen. So here you see that green arrows. So this is the green arrows. So this happens only the reaction carry out under the non-aqueous reaction conditions. So resulting that you will get the tertiary carbocation. So after that a ring contraction takes place. So this carbon-carbon bond breaks down. Then after that this bonded electrons moves towards to the carbocation center, leads to the ring contraction takes place. So after that generates the one new tertiary carbocation center. Then followed by that electron shifted towards to this carbon, then followed by this electron shifted to this carbon. So resulting that generation of new carbocation center, then followed by a ring expansion takes place. So this bonded carbon-carbon bond breaks down, this bonded electron moves towards to the carbocation center, leads to the ring expansion takes place, which generate this tertiary carbocation, then followed by aromatization takes place, which leads to the para product. So para product means that this one is ipso, so this one ortho, this one meta, this one para. So our rearrangement takes place at the para position. So in the way, our solvent, selection of solvent highly influences in the selectivity of the product. So the overall driving force for this particular Dienone-Phenol rearrangement is aromaticity. That migratory aptitude of this Dienone-Phenol rearrangement has H hydrogen has more priority than phenyl as well as alkyl. In case of alkyl, tertiary alkyl will get more priority and followed by secondary and primary. So when you think about electron withdrawing and electron donating group point of view, electron withdrawing group will get more priority than electron donating group. And similarly, when you see the electronics of dienones, resonance will get more priority than the hyperconjugation and plus I effect. So when you get your free time, you will give a shot to these following problems. So when you get your when I get a chance, I try to work it out these problems. I will make another video of about these problems. So we already discussed a series of esterification reaction. If you missed these videos, please you just log on our K-Markham channel. You can find all these esterification videos and also PDF link of this particular reaction you can find in the description box. So finally, thanks for watching.